Yay or nay? Is this proper?
Yes, it's proper.
Okay, thank you. So we don't need to do long division. We can just kind of jump right in. All right, we have a rational expression we're trying to integrate. It's pretty complicated. I don't just know it off the top of my head. I can't do a U sub. So let's try partial fraction decomposition. So we're going to factor the denominator as much as possible. So I'm going to have 2x squared minus x plus 4 over. I can factor out an x, and I'm left with x squared plus 4. Okay, can I factor that any further? No. So we have one linear factor. And then again, this was, I just showed you in that example why x squared plus 4 is irreducible, right? All right, so we're going to break this out into two partial fractions, a over x. And then my second partial fraction has an irreducible quadratic in the denominator. So I need to do a numerator that's linear. So I'll do bx plus c. All right, what's next?
You multiply by the common denominator.
Good, both sides get multiplied by that x times x squared plus 4. On the left-hand side, that's just going to leave me with the numerator, 2x squared minus x plus 4. The right-hand side, when I multiply the first term, the a over x, the x's cancel, and I'm left with a times x squared plus 4 plus bx plus c. Now the x squared plus 4's cancel, and I'm just left with x. All right, so you can use the little trick we had to speed things up, but this is where it becomes a little more dicey because you're not going to be able to use it the whole time. So for example, I could let x equal 0. And that's going to cancel out that entire factor, right? And that'll leave me with what? I'll have just 4a on the right, and on the left I'll have 4. And now I know that a is just 1, right? So I could rewrite my equation as 2x squared minus x plus 4 equals, now a is just 1, so that's just x squared plus 4. And I'm going to distribute my x, so I'll have bx squared plus cx. But now there's not really any values that you can plug in for x that would eliminate, right? For example, b, but not eliminate c. The only thing that would eliminate one of them is 0. We already tried that, and that's going to get rid of both of them, right? So you can do this a couple ways. Remember, at this point, you can let x equal any other value. So if I did that, if I let x equal 1, I'm going to have an equation left in b and c. And then I could like let x equal -1, and I'll have a new equation left in b and c. And now I have two equations that involve b and c, and I can just solve it as a system of equations. Or we can kind of go back to the other way we used to do things, right? So I can group So I'm just moving things around here. Now on the right side, if I factor out x squared, I'll have b plus 1. And so now I can set coefficients on either side equal to each other, right? So if these two sides of the equations are equal, then their coefficients have to be equal. So the x squared coefficients have to equal each other. That gives me b plus 1 equals 2. The linear coefficients have to be equal, so that gives me c equals -1, and then just solve. So b also equals -1, right? No, b equals +1. Hey, update. Come on, screen. There we go. Okay, so now let's rewrite our integral using our partial fraction decomposition. What we end up with is basically, I'll circle it over here in red, that's our decomposition. Now we're going to plug in values for a, b, and c. So we get the integral of a was 1, so I have 1 over x. Whoops. Okay, then b is 1, so plus x. C is -1, minus 1 over x squared plus 4 dx. Siri, no, Siri, go away. Siri, turn off. Damn it. All right. So now let's see how to deal with this, right? Antiderivative of 1 over x is just natural log absolute value x. So that's that piece. Now I'm going to break the other piece into two separate integrals. So I'm going to still have the plus integral. I'm going to do x over x squared plus 4, and then dx minus integral 1 over x squared plus 4 dx. All right, ideas on how to deal with that integral. Come on now. It's just a Calc 1 integral. I'll tell you that. There's a hint. Okay, I'll just take Alex is signaling at the computer, and I think he's saying u sub. It is just a u sub. So here we can let u equal the denominator, x squared plus 4. And then du is 2x dx, right? So we don't have 2x dx, but we do have x dx right there, right? So we can just divide over the 2. So half du is x dx. So that integral becomes, right, 1/2 integral of 1 over u du, which is then half natural log absolute value u, which is half natural log x squared plus 4. Now, technically, it's absolute value x squared plus 4, but because x squared plus 4 would always be positive no matter what the input is, we can drop the absolute value at that point, right? All right, so let's go. Here's what we have. Natural log absolute value x plus half natural log x squared plus 4. Now this last one is actually one that we know, and it'll come from, I gave you that table of important integrals, didn't I? Plus 1 over 2 inverse tan of x over 2 plus c. Good? All right, give me a green check when you're done with that one.
Would it be minus 1/2 inverse tangent?
Is it negative 1 over a and I just didn't?
No, but weren't we subtracting it?
Oh, we were. Thank you. I'm sorry. I just dropped the negative. You're right. Okay. Everybody good? All right. So hold on. Let me look at this one to see if it's one I want to do or if it's one I don't care for. Yeah, we're going to skip this one. All right, on to case 4. So this is our last case. Remember how we started? We did, how do you deal with rational expressions when your denominator factors to first distinct linear factors, so unique linear factors, and then how do you deal with it when you have repeated linear factors? And the third one was, okay, what do you do when you have distinct irreducible quadratic factors? And so now it's, what do you do when you have repeated irreducible quadratic factors? And it is very much the same idea as what we do when we have repeated linear factors. It's just now, if our denominator is irreducible quadratic and it is repeated, my numerator needs to account for that by being linear. So I'm still going to build up my partial fractions until I get the highest power of the repeated quadratic factor. So it'll make more sense when I show you an example, but I'll give you a minute if you're trying to write this down. Give me a green check when you're ready to move to the example. So we're not going to do any calculus with this one. We're just going to write out the partial fraction decomposition. So we're going to take this and we're going to set it up like we are about to decompose it, right? And we're going to just stop there. All right, so let's see what we have. We get the denominator's already factored for us. We just need to make sure it's completely factored. So the first term is linear. Second term is linear. Third term is quadratic. Let's just make sure it's irreducible. So I can do that by looking at, all right, what's b squared minus 4ac? Well, that would be 1 squared minus 4 times 1 times 1, which is -3. That's less than 0, so it is irreducible, right? And then the last one, we already showed that factor, x squared plus 1 is also irreducible. So this is completely factored. If I were going to set it up to decompose into partial fractions, this is how we would do it. X cubed plus x squared plus 1 over x times x minus 1 times x squared plus x plus 1 times x squared plus 1 cubed equals. All right, so help me out in the chat. What's my my first partial fraction going to be set up like? We'll just go in order of the factors in the denominator. What's my first partial fraction going to be?
A over x.
That's it. The first one is just linear, so it's just a constant over x. All right, keep going. Next partial fraction. My next factor is x minus 1.
Just be b over x minus 1.
Good. B over x minus 1. Nope. All right, someone new. What's the next one? My next partial fraction is now an irreducible quadratic.
Going to be a2x plus b2 over x squared plus x plus 1.
Yes, or yeah, I'm going to just keep going. If we're going to use subscripts, I would just do all A's. But if we're going to use the alphabet, then I would just keep going down the line. But yes, you're correct. So I'm going to do cx plus d over that irreducible quadratic, x squared plus x plus 1. All right. Now, we have another irreducible quadratic, but this is a repeated irreducible quadratic. So do you guys remember what we need to do when we have repeats? What we did with the repeated linear factors last week. You have to build the partial fractions up until you get to the highest power of the repeat, right? So Tommy, what do you think this next one would be?
EX plus F over x squared plus 1.
You got it. EX plus F over x squared plus 1. There's going to be 2 more. Who knows the next one? Emin, Alex, Kaylin? Oh, you guys are just going to ice me?
gx plus h over x squared plus 1.
So gx plus h, I agree with that one, over x squared plus 1. But now we do squared. And then what's the last one?
Ix plus j over x squared plus 1 cubed.
Good. Ix plus j over x squared plus 1 cubed. What we had to do was account for all possibilities of denominators, because you're going to need this one for sure, meaning I and j, one of those has to be non-zero, right? But these ones are also possible because the common denominator between those partial fractions would still give you this as a common denominator, right? They're not necessary, meaning if E is 0 and F is 0 and G is 0 and H is 0, then these are gone. And the common denominator of what remains is still the common denominator that we have, correct? But those have a possibility of being non-zero because the common denominator of all of those is also still that common denominator that we have, right? So we're just accounting for those as possibilities. Does that make sense? we're not gonna do calculus with it. It's
Wait,
just,
I'm not sure if you already said this, but why wouldn't it be like E2x plus F2 and then E3x plus
you could do
F3?
that. That's just naming conventions. They just
Oh.
represent different coefficients. All I
Okay.
was saying is that be consistent about your naming convention. So if you want to go with subscripts, then just like use all A's and start with A1, A2, A3 up to whatever A9. It wouldn't be wrong. It would just hurt me to look at because of notation stuff. Cool. Let's practice just setting this up to decompose like we did the last one. I won't make you find the integral, but take a moment, set it up to decompose, and then I'm going to go around the horn and call on you guys to tell me how it should decompose.